Okay, so let us start. In the previous lecture, two lectures, we gave some heuristic and invading arguments why the relativistic quantum theory should be local theory and why it should be quantum field theory. And now we will start to study such a construction. As I promised you, we will follow the Weinberg approach. That means we shall first define what particles are, and from the particles we will come fields, and to field interaction and particle interaction will be described in terms of fields. And after that will be done, we will use another approach, the top-bottom approach, using methods for quantizing fields, and we will meet these two approaches, and we will see that both approaches will lead to the same results. So before we start this program, let us give some small brief recapitulation of quantum mechanics. So we will recapitulate what you already know, since of course quantum field theory is based on the same principles as quantum mechanics. So you know that the systems in quantum mechanics are described as using Hilbert space, and this Hilbert space is assumed to be separable. That means that there exists a countable basis in such Hilbert space. The states of the system are described by vectors in such a Hilbert space, and these state vectors can differ by phase, and all the vectors which differ by such a phase describe the same state. So it's sometimes stated as the statement that the states are expressed in terms of rays in the Hilbert space. These rays are just such a sets of vectors which differs by the phase. So these are states, and we need also observables. And these are described by self-adjoint operators. Self-adjoint operators, which are linear operators, of course, and the self-adjointness means that we have relation O cross equals to O, where the Hermitian conjugated operator or adjoint operator is described in the usual way. If we have two vectors in the Hilbert space, the matrix elements of the adjoint operator is nothing else but transpose matrix elements of the original operator, complex conjugated. If we measure some observable O, we expect that this observable, because it is self-adjoint operator, has a set of eigenvectors and eigenvalues, and the measurement of such an observable can give as a result only these eigenvalues. If we measure such an observable repeatedly, we can calculate the mean value of such an observable, and this in the state psi, and thus this mean value can be obtained by sandwiching the operator by this state. We can also calculate the probability of measuring the eigenvalue lambda n when a system is described by the state psi. And this probability can be obtained as a square of the amplitude of probability, which we obtain as a scale product of the eigenstate psi n corresponding to this eigenvalue lambda n with the state vector psi. And the probability is square of the modulus of such an amplitude. Of course, this is true only when the lambda n is non-degenerate. In the case when lambda n is degenerate, that means there exists more than one eigenvector with the same eigenvalue lambda, n, then we get such a probability as a sum of these probabilities. And this can be rewritten also in terms of sandwiching some operator, we call it pi n, which is given as a sum of one-dimensional projectors to the eigenvectors with the eigenvalue lambda. So Pn is such an operator. And this operator is an orthogonal projector and has very pleasant properties. It is Hermitian or self-adjoint, and its square reproduces this operator. As far as several observables are concerned, say observable O and observable O prime, when these observables commute, it is possible to measure these observables simultaneously, and this mathematically means that there exist common eigenvectors psi n, which are eigenvectors of both O and O prime. That means O psi n gives some eigenvalue, call it psi n, and O prime psi n give some eigenvalue psi prime n psi n. So we can form a basis in the Hilbert space from the eigenvectors which are labeled by the eigenvalues psi n, psi prime n, and probably a lot of other eigenvalues of all the operators which are commuting with this O and On. Such a system of operators which are all commuting and which have the property that there exists just one basis vector to each set of eigenvalues of these operators. That means such set of eigenvalues are non-generate, is called the complete system of commuting operators. You probably know such complete systems of commuting operators. For instance, for one particle with spin 0, such a complete system of commuting operators are the operators corresponding to x coordinate, y coordinate, and z coordinate. And the basis in the Hilbert space, non-degenerate basis in the Hilbert space, is spanned by the vectors which are labeled by eigenvalues of these three commuting operators. Let us now describe the time evolution. Time evolution is described by Schrödinger equation, as you know, in our units, can be written in such a form, where H is a special operator, known as the Hamiltonian operator. And of course, this is a differential equation of the first order in the time derivative. So you need the initial condition. Think, for instance, t equals to t0, get psi 0. This is the initial condition. And the solution of such equation can be formally written in terms of acting by so-called evolution operator on the initial state. And this evolution operator, Hamiltonians, which are not explicitly dependent on time, can be obtained by exponentiation of this Hamiltonian. In the general case, even when the Hamiltonian is dependent on time, then instead of such a simple exponentiation, we get t exponents of integral from t0 to t dt h. There are several important properties of this time evolution operator. The first one is the initial condition. At t equals to t0, the initial time, this operator should be 1 because it should reproduce this initial condition for the time evolution. The time evolution should be unitary. That means t0 cross t0 is the same as u cross t0 u t0 should be 1. This is important property because it expresses the conservation of probability. That means that the norm of the vector psi t is conserved. Constant is independent on time. And we have also the so-called semigroup condition for this time evolution operator. And this semigroup condition tells us that if we have some time evolution from initial time to some intermediate time t prime, and then time evolution to the final time t, we have such a relation. So this is valid whenever t0 is smaller than t prime, smaller than t. Of course, from the formal solution for the evolution operator for the Hamiltonian, which doesn't not depend on time, we see that the evolution operator can depend only on the difference of the times, t minus t0. So the time evolution is the same when we both shift t to t plus some a and t0 shift t0 plus some a. This means that it doesn't depend on the moment when we start the experiment. If we measure the time evolution from any initial state, initial time with the same initial state, the result of the time evolution will be the same after some time t, which is difference between the initial time and the final time. Well, the picture of time evolution I have shown you yet is called Schrödinger picture, as you know.
Hello, I'm sorry for interrupting, but my friend is trying to join the session.
Okay.
Let him in.
Okay. I can't see him. Ah, I see him. Okay. Fine. Everything is okay?
Yes, thank you.
Fine. So the picture of time evolution I have shown you yet is the Schrödinger picture. There exists also the Heisenberg picture, as you know. And it is in some sense opposed to the Schrödinger picture, because in the Schrödinger picture, the operators, provided they have not explicit time dependent, are not subject of time evolution, while the state change time. On the other hand, in the Heisenberg picture, operators depend on time, and the states are time independent. The basic idea is, of course, known to all of you. If we would like to calculate, for instance, some matrix elements of operators in time t, we can use the Schrödinger picture so that observable O doesn't depend on time, but the states are time dependent, and we can rewrite this time dependence as a solution of the Schrödinger equation using the evolution operator. And we can now interpret this combination of operators as time-dependent Heisenberg operator. So instead of letting evolve the states, we let evolve the operators, and the matrix elements of the operators calculated at time t can be either calculated as sandwiching the Schrödinger representation of the operator O by the time-evoluted states, or by sandwiching the Heisenberg operator at time t with states, which are the initial state of our problem. So, in the Heisenberg representation, the measurements are localized at time t, and the states are localized at the initial time t0. Of course, such a definition of Heisenberg operators depend on this initial time t0, and we can, of course, use another initial time t0 prime. And in order to have the same matrix elements at time t, we should introduce new operators O primed t, which are connected with the old Heisenberg operators just by evolution from t0 to t and t0 back. So these operators have the same matrix elements, t0 primed. So we can either use such a Heisenberg operators and the state at t0 primed, such operators initial state at t0. So, because the relativistic quantum theory is our construction of relativistic quantum theory will be based basically on symmetries, we should also remind you the role of symmetries in quantum mechanics. The symmetries are implemented in quantum field in quantum mechanics in terms of mapping from the rays in the Hilbert space, which correspond to states, again to the rays of in Hilbert space. And the symmetry is not arbitrary mapping, but a mapping which preserves the probability transition amplitudes, or the probability of measuring the state psi n in general state psi. This probability is given as a square of corresponding amplitude, and the conservation of probability means that if we make the mapping, this square of modulus is not changed. There exists a powerful theorem, known as Wigner theorem, which states that we can describe such a probability conserving mapping between rays in Hilbert space in terms of operators acting on the vectors in the Hilbert space. And these operators are either unitary operators or anti-unitary operators. You of course know what is unitary operator. This is a linear operator which has the property that it preserves the norm of the vector. So if we have two vectors, its scale product is preserved by unitarity transformation. This is the case when the operator U is unitary. And this can be also expressed in terms of adjoint operator. In the case of anti-unitary operator, the scale product is preserved up to complex conjugation. Of course, in order to satisfy this, the operator U should be antilinear. That means that if we act with such an operator on a linear combination of some vectors, we get again linear combination, but with complex conjugated coefficients. Again, in this case, we can describe this property, this defining property of anti-unitary operators by means of such relations. But we have to modify the definition of the adjoint operator of antilinear operator. If U is unitary or linear, we have such a definition of the matrix elements of adjoint operator. In the case of anti-unitary operator, this definition is preserved up to complex conjugation. So, or we can say that the matrix elements of the adjoint anti-unitary operator is the transpose matrix element of the original operator. So we have defined the symmetry as a probability conserving mapping between rays in the Hilbert space, and we can ask what is the effect of such a transformation. We already know that on the vectors, this symmetry operator acts by usual way, and we have also action on observables. And this definition is motivated by the demand that the matrix elements of the transformed operators between transformed states is the same as the original matrix elements of the original operator between original state. That means that transformed operator by the symmetry is U, O, U cross. Then, of course, psi cross, psi primed, O primed, phi primed is the same as psi, O, psi. Okay, so if we interpret symmetry in this way, this is nothing else but change of the description of our system. Instead of using system of states psi and operators O, we use systems of state psi primed and operators O primed, and we have a relation between these unprimed and primed objects. But if we, so we can say we have one physical system and say two people who would like to describe this physical system. One uses the state psi and operator O. Second uses state psi prime and operator O prime, and the physical output of these two descriptions is the same. So probabilities and matrix elements are the same. So when such a change of description is called symmetry. It is the case when the most important operator for our system, the Hamiltonian, which is connected, as we know, with time evolution, is invariant with respect to such a transformation. That means H prime, which is U, H, U cross for the symmetry operator U, doesn't changes under symmetry. This has very, very important consequences, because in such a case, both these observers that using this formalism or this formalism have the same Hamiltonian. That means the same Schrödinger equation, and the description of time evolution is the same in both the description for both operators. We can imagine this situation as a situation of two observables in two different inertial frames. The two observables uses the same Hilbert space, the same Hamiltonian, but there exists some transformation between the states in both descriptions. The same state of the physical system is described either by psi primed, but the time evolution described by both these observers is the same. The Schrödinger equation has the same form. This is nothing else but the passive interpretation of the symmetry. There is also the second one, the active interpretation. And this active interpretation is opposite to this. We have only one observer, and we use this operator U to transform our states. So here is state psi, here is state psi primed, this U times psi, and these two vectors correspond to two different physical states of the same system, of some system. So in terms of active interpretation, make active transformation of the state of the system. For instance, we boost some elementary particle originally from zero velocity, which is non-zero. And we also make measurements of the system by means of making the same transformation also on physical apparatus, which we use as a measurement. Other possible example of such an active interpretation is, for instance, taking particle with spin oriented in some direction, say in the direction of the third axis, and we make a rotation, and the new state of the system will be orientation of the spin in some general direction. And when this transformation given by U is symmetry, this active interpretation of it means that if we transform both the initial state and the final state, the time evolution, the probability or amplitude of the probability will be conserved. Let us be more detailed. Say we have some initial state and we have some final state. And we are interested in the measurement which is described by the amplitude of time evolution from initial time to final time t. That means this amplitude describes the amplitude of probability of finding the system which was in initial time t0 in initial state I in the state f. So we can, let us denote this amplitude as mfi, and let us calculate this mfi in two possible ways. The first one is, for instance, we do not let the Hamiltonian to depend explicitly on time, so time evolution will be simply given by exponential of t minus t0 acting on I. And let us calculate the probability amplitude between the transformed state. So we, for instance, two states of the particle with spin oriented in some direction, or particle with spin, and then we rotate both the initial condition and also rotate the apparatus measuring the final state. So let us calculate such an amplitude. So we must transform both the initial state and the final state. And provided U is unitary operator, then we can use the definition of the Hermitian conjugated operator, and we get such expression. But provided U is symmetry, then U cross H U is again H. And we can imagine, for instance, Taylor expanding this exponential and writing the nth power of the Hamiltonian sandwiched with a U cross and U as a U cross H U, U cross H U, and so on, U cross H U n times. And we find that this is nothing else but Hamiltonian to the nth power. So applying this trick to all the terms of Taylor expansion of this exponential, we get in the end that our amplitude is exponential of I U cross H U t minus t0 I, or f, because this is again the Hamiltonian, exponential of I, so it should be, it's minus here, h t minus t0 I. So we end with the following relation. That means the probability amplitude of the transition from the state I to the state F and to the transform state I and transform state F is the same. What about the case when U is antiunitary? Then we have to be a little bit more careful. Of course, we can write M F U F U I S F U F exponential of minus H I t minus t0 times U I. But now we have to use the definition of the antiunitary operator, and we know that this can be written as F U cross this exponential, but complex conjugated. Now we can use the same trick as we did here, but because the U is antilinear operator, we must be careful when we commute this operator with this imaginary unit. Commutation here means change of the sign, so that to be careful we must use such a relation. And now, because we suppose that U is symmetry, this is again the original Hamiltonian. So we get from this that this matrix element is exponential of plus I H t minus t0 I and complex conjugated. And this complex conjugation can be easily done. We simply Hermitian conjugate this as a set of objects which can be conjugated Hermitially. That then means that we get I Hermitian conjugated of this. This Hermitian conjugated is simple because H is Hermitian operator. The only change is this sign, because we have here imaginary unit. So we get exponential of minus I H t minus t0 F. And comparing this with the original amplitude, this one, we see that we have such a relation from antiunitary operator. The amplitude between transform state is the same as amplitude between the initial and final state, but in different order. So we see that whenever the symmetry is described by anti-unitary operator, the time evolution is surrounded by time inversion of the time. Okay, so of course you know this. This was only to remind you how does it work. And because for us it will be very important to use special symmetries, we have to discuss how these symmetries are connected with the groups. Let us remind you the definition of the group. You know that the group is a set of elements, and there is a binary operation on such elements, which two elements G1 and G2 assigns its product, G1 times G2. And this product have the following properties. The first one is existence of the unit element. That means there exists some E as G, for which and for every other G in this set of G, of this group, we have E times G is G times E is G. The second property is the associativity. That means if we have three elements, G1, G2, G3, which is G, we can calculate first G1, G2, and then G3, or we can calculate first G2 and G3 and multiply it by G1, and the result is the same. And last property is the existence of inverse element. That means for every G, there exists an inverse element, which has the property that G times G to the minus 1 is G to the minus 1 G. This is the unit element of the group. Of course, you know this, and how such an algebraic structure can be promoted to the Hilbert space of states of quantum system. So in such a case, for element of G in group, we have unitary or anti-unitary operator, which we call UG. In such a case, the symmetry group is implemented on the Hilbert space of states of the system. And because the symmetry is in fact the correspondence between states of the system, and states are described by rays in Hilbert space, the algebra of the symmetries can be expressed by the following relation. This transformation corresponding to two elements of the group should be composed to transformations G1 times G2, because we suppose that the algebraic structure of the group is preserved on the Hilbert space. But since the states are determined up to a phase, there should be and could be a phase which depends on both G1, G2, and probably also on the state vector psi, on which this product of two symmetries act. There is an interesting theorem which tells us something about this phase. This phase, in fact, doesn't depend on psi. Why it is so? Let us try to apply this equation to a sum of two vectors, say psi1, psi2. According to this composition rule for these two symmetries, we get on one hand u G1 times G2 times phase, which depends on G1, G2, and psi1 plus psi2, and acts on psi1, psi2. And the second possibility how to rewrite this left-hand side is to use that this operator is either unitary or anti-unitary, and that means that we can write it as G1 times G2 acting on psi1 plus UG1 UG2 acting on psi2. And again, we can use this composition rule for the symmetries, group relation, and we get that here we get U G1 times G2 times phase E I, which depends on G1, G2, and psi1. And the second term is the same, G1, G2 times phase, now depending on G1, G2, and psi2. This is acting on psi1, this is acting on psi2. So comparing the left-hand side and right-hand side, that means this result and this result, and multiplying both these sides by inverse, because this is unitary or anti-unitary, so it has inverse, G1, G2 cross the left-hand side, we get the following relation, E, I, theta, G1, G2, depending on psi1 plus psi2, times psi1 plus psi2, and on the right hand side, using linearity of these, antilinearity of these operators, we can obtain here again e to theta g1 g2 psi1 times psi1 plus e to e theta g1 g2 psi2 psi2. And if we suppose that psi1 and psi2 are linearly independent, then we can compare the coefficients at psi1 and psi2 on both sides of this equation. So we get, and I will not to write e to theta, but just the relation for thetas. So theta g1, g2, psi1 plus psi2. This is the left-hand side, and on the right-hand side we get either theta of g1, g2, psi1, or theta of g1, g2, psi2. First case corresponds to comparing the coefficient at psi1, and the second corresponds to comparing coefficient at psi2. So we see that in order to satisfy such equations, the phase theta is in fact independent of this psi1, psi2. The result is that the composition rule, which corresponds to the group multiplication, is implemented on the Hilbert space in terms of so-called projective representation. You probably know the ordinary representation of the group, which has this phase equal to 0 for every G1, G2. But because the states are described by arrays, not just by vectors, this phase is possible because the state on the right-hand side, which differs only by a phase, describes the same state in the Hilbert space. Well, this possibility of the phase and the projective representation is a well-known feature of quantum mechanics, and it has its application also in quantum field theories. In many cases, this phase can be removed by proper redefinition of these operators UG. So from now on, we will suppose that we are dealing with ordinary representation and we will omit this phase. So let us now recapitulate some basic facts about Lie groups. You probably know all of I will be telling now, but the reason for this recapitulation is to introduce notation and terminology. So as you know, Lie groups are groups, element of which are parameterized by continuous set of parameters. Symbolically, this theta is a set of parameters theta1 to theta d, and this d is called dimension of the Lie group. And such a parameterization satisfies some composition law. So if we have two elements of the Lie group which are parameterized by set of parameters theta and theta prime, we get some element of the group which is described by the parameter which is some function of these parameters theta and theta prime. It is a nice exercise which you probably do during the seminar. This composition law of theta prime have to satisfy several conditions. The first one is that if we appropriately define that the unit element corresponds to the case when all the parameters are 0, then this function of two sets of parameters, have to satisfy the following equation. That means this is nothing else but the consequence of the definition of the unit element. The second useful condition for this is the consequence of associativity. That means if we first compose parameters theta prime and theta, and then make a composition with group element with parameter t double primed, we get the same as we first compose group elements with parameters theta prime, double primed and theta prime, and theta. So the proof of this is almost straightforward, so I left it to the exercises, to the seminar. And straightforward consequence of these is that this function of theta and theta prime, I call it function, but in fact, because these thetas are d-dimensional multiple of parameters, so also this f is a set of d functions, so we can assign to this f an index as we did for the parameters, and this index goes 1 to d when d is dimension of the group. And if we try to Taylor expand this function, there is no constant term because of this, and the only possibility for the linear terms in the parameters are the sum of them, and the quadratic terms in this theta and theta prime should look like ki jk times theta j theta prime k plus higher order terms. It is clear that it must be so, because if we admitted also terms theta I squared, or theta I theta j, or theta k squared prime squared, or theta k prime theta k l, then this first condition, it should be satisfied by these functions f, would not hold. These terms are not allowed, and up to quadratic terms we have such an ansatz for this function. These are some up to now unknown constants. Now suppose that our Lie group is represented on our Hilbert space. That means that we have assignment to each element g, which depends on theta, some unitary operator u g of theta. And since we assume the smooth dependence on these parameters theta, we can write that this g as a function of the parameters of theta is what? For theta equals to 0, we have g 0 equals to unit element, and then zeros all the term in theta should be unit operator. Then we have some linear terms which we write in the form with some operators ta, and conventionally we use here I, and also some quadratic terms. Let us write them as theta a, theta b times some operators tab plus higher order terms. Of course, since this u is supposed to be unitary, then these operators ta must be Hermitian. It is easily seen when we rewrite, which must be 1, And if we make a Taylor expansion of these up to the quadratic terms, the linear terms have to cancel because we have 1 here. And as a result, this is possible only when such a relation holds. Here, these operators TAB have to be symmetric. It is clear because this product theta A, theta B is symmetric with respect to exchange of A and B. Here, of course, the summation over repeated indices is strictly assumed. Let us now calculate what happened if we take a product of two such transformations corresponding to two different sets of parameters. So we get, according to this Taylor expansion, 1 plus I theta A TA plus 1/2 theta A theta B T A B plus higher orders times the same for primed parameters TC times TC, sorry, plus 1/2 theta prime C theta prime D TCD plus higher orders. And this gives us up to the terms which are quadratic in the parameters, simply 1, this is this term, plus I TA times theta A plus theta prime A, sorry, plus the mixed terms, which comes from this one and this one. And of course, the other quadratic terms, this is this term and this term multiplied by the identity in the corresponding parentheses. So we get 1/2 theta A theta B plus theta prime A theta prime B times T A B plus higher order terms. So this is one way how to calculate this product and how to obtain the Taylor expansion of this product in terms of the Lie group parameters. And the other way is to use our composition rule so that the same is also U of G theta times G theta prime. And for this, we have composition rule inside the Lie group, so we get U of G of F of theta and theta prime. So if we use this and take this composition of parameters theta and theta prime as the parameter theta here, we get 1 plus I times F theta theta prime A TA plus 1/2 F theta theta prime A F theta theta prime B TAB plus terms which are higher orders in this F parameters. And now we can Taylor expand this F, and we have here the corresponding expansion. So we get 1 plus I TA and theta A plus theta prime A plus K A B C times theta B theta C plus higher order terms and expansion. And here we can expand only to the first order because this term is already quadratic in F. So we get 1/2 theta A plus theta prime A times theta B plus theta prime B times T A B plus terms which are higher order. So in the end, we get 1 plus I theta A theta A plus theta A primed plus terms which are quadratic in theta, 1/2 theta A theta B T A B plus similar term which is quadratic in theta prime A theta prime B T A B plus mixed terms. And these mixed terms consist of this term, theta B, theta A, theta B times K A, B, C, D, C. This is this term. And also the terms coming from cross terms in this product. And since TAB is symmetric, we have twice TA, TB primed times 1/2. That means plus TAB. Of course, I probably something missed. And this is, okay. So, and this is the second way how we calculated the same. The first result was this one. So this must be 1 plus I TA theta A plus theta A primed. This is this term. Plus this quadratic terms. 1/2 TAB theta A theta B plus theta primed A theta prime B. And the mixed term minus theta A, theta A theta primed B times TA TB. So comparing these two expressions, we get interesting relation. We see that these terms cancel each other, these terms cancel each other, the quadratic terms cancel each other, and we have the following operator relation. It should be primed when we compare this one and this one. So minus TA TB must be KAB C TC plus TAB. And this is a very interesting result because we see that if we know the composition law in terms of F, because this K was a parameter which described the composition law of the parameters of the Lie group. So if we know this case, the composition law, we can express these TABs, that means the quadratic terms in the expression of the unitary operator representing the corresponding group element with parameter theta in terms of product of the linear terms in the corresponding expansion. We have here linear terms, here is quadratic term, and these quadratic terms are related to the linear terms, as we have seen. And it is possible to continue this game and, in fact, express all the higher order terms which we have omitted here, which should be higher order in these parameters, and the coefficient will be some operators. So these operators, which are coefficient at higher order terms, in terms of these linear terms. So these linear terms are very important for us. These are called generators of the group, of the representation. And these generators obey very well-known commutator algebra, which can be derived from this equation. We simply know that this TAB must be symmetric because this was terms which describe the quadratic terms in the expansion. So we can write this equation and analogous equation with A and B interchanged. So we get minus TB TA, which is K B A C TC plus TBA, but this is the same as TAB due to symmetry. And if we subtract these two expressions, we obtain the following relation. TA, TB, this commutator of these operators on the Hilbert space, is, I have missed some I here, I'm sorry. And this I should be at this K. So this must be multiplied by this I. So whenever we have I, we should write it here and also here. And we see that this can be written as I times K BA C minus K AB C times TC. And this object is called the structure constant of the Lie group, and the corresponding notation is FAB C. And of course, the left-hand side and the right-hand side is antisymmetric, so this structure constant must be antisymmetric. with respect to exchange of the upper indices A and B. So this is well-known fact, and we will use it in what follows intensively. So these structure constants are in general case non-zero, but in the case when these structure constants are zero, we call the group abelian group. And in such a case, the composition law for multiplication is simply theta I plus theta I prime. In the case of abelian group, we have the possibility to express the UG theta, the corresponding unitarity operators, in terms of operators TA, of the generators. Can we do it? So we know that for finite theta, we can take as a parameter, instead of theta, parameter theta over n, and n goes to infinity. And in such a case, we know that operator u can be written as 1 plus I ti times parameters, theta a over n, plus terms which are quadratic, this parameter, but if n goes to infinity, we can omit these terms. So roughly, for n going to infinity, we can write such a representation of this element, of the representation of the element of the group. And of course, if we calculate representation of elements G with parameter theta over n to the nth power, on one hand, on the grounds of the group multiplication, and using this composition law, we see that this is nothing else but G of theta. Simply G theta over n to the second power is nothing else than G of theta of f of theta over n, theta over n. According to this composition law, we get G of theta over n plus theta over n, and we can iterate this to get that G theta can be written as G theta over n to the nth power. On the other hand, we can express this as 1 plus E ta theta a over n to the n power, because we have composition law corresponding to the representation on the Hilbert space side. And when we set n to infinity, we can calculate this limit, and it is nothing else but the exponential. So, in the case of abelian group, we have a very nice parameterization of our representation in terms of generators, this exponential parameterization. Also, in the case of non-abelian groups, if f, a, b, c is non-zero, it can be shown that if we cleverly define the parameters of the group, so clever choice of this parameters theta allows us to write the same equation. That means U g theta is exponential of I theta a ta. But this is a matter of choice, whether this is possible in such a way. Of course, these parameters of the Lie group are not unique. The only what we needed for our consideration was the constraint that at origin it parameterizes the unit element. But we can make any wild nonlinear transformation which preserves this condition. And of course, all these functions f will be changed, all these k's will be changed, the definition of ta will be changed. But in the end, with clever definition of these parameters, we can even, in the case of non-abelian group, achieve such a exponentialization of the unitarity operators in terms of Hermitian generators. Okay, so we have run out of time. So I will probably stop here. It is time for questions and remarks.